Hi, while I'm making videos, I'm gonna just make one more, and then I should go to my talk. That would be good. So yeah, you probably hear a lot of murmuring, whatever in the background. Sorry about that. This is as quiet as I could find. I'm sitting on the floor somewhere in this big building. Okay, I'm treating 11.3 fairly lightly. It's nice. These inequalities, the Markov and Chebyshev inequalities, they're used to give you bounds on probabilities. And this is usually you don't know the distribution of a random variable, and you just kind of want some estimate of a probability. So this could be nice at giving you upper or lower bound or something like that. So, um, you know, you'd hope you know the distribution, but if you don't, this gives you at least something. So the Markov's inequality says let x be a non-negative random variable, then for any t, the probability that x is bigger than or equal to t is its expected value over t. So it's a very general result. Here's an example. A secretary can handle 8 documents per day, so that's the mean. So this is expected value of x. What can be said about the probability she will handle at least 12 tomorrow. So we had a similar problem, I think in homework set 6, but we knew the distribution of how many documents she could do per day was Poisson. But we don't know that here. We can assume, but we don't know. So best I can do is get an estimate. We don't know the distribution, okay? So we must get an estimate. So what's the probability that she can finish more than 12 documents tomorrow? That's, less than or equal to, we expect her to be able to do 8 divided by t is how many she's doing, 12. 4 and 4, right? This is 2, 4, 4, 2/3. So the probability she finishes is at least 12. There's a 2/3 chance. So it's just an estimate. That's all that is. So I don't really have a lot. Just one page for this section, which is kind of rare. For any section I've done, right? Now Chebyshev's, similar, but at least here you would have to know, you would know the mean and the standard deviation. You can say maybe a little bit more. Let x be a random variable with expected value mu and variance sigma squared. Then for any k bigger than 0, the probability x minus mu is more than k standard deviations is less than or equal to 1 over k squared. The probability that x is within k standard deviations of the mean is 1 minus 1 over k squared. So again, just two statements about if you know the standard deviation, to put an estimate on what's the probability within so many standard deviations of the mean. Now, I mean, we know this if we had a normal curve, that within one standard deviation is about 68%, within 2 standard deviations about 95%, but I don't know necessarily I'm going to have a normal distribution. All I know is x is a random variable, here's the mean, here's sigma. So don't be tricked to be thinking automatically that, oh, I have a normal. I think it's very natural to think that way, especially after the last section, but if you just have one random variable, you have no idea. So let's go, let's leave that up there a little bit. So let's do one application here, a little bit more. A secretary can handle 8 documents per day with a standard deviation of 1 document. Okay, a little bit more information. What can be said about the probability she'll finish between 6 and 10 documents tomorrow? So that is really 8. That would be 2 standard deviations to the left and 2 standard deviations to the right. So we're answering what's the probability that the number of documents she'll finish, the mean is 8, is less than 2 times 1 within 2 standard deviations, right? And that's bigger than or equal to 1 minus 1 over k squared. K is 2, so that's equal to 3/4. So what's the probability she'll finish between 6 and 10 documents tomorrow? There's a 3/4 probability that will happen. Again, if I knew the distribution, I could find out exactly, but this is just an estimate. I think that might be all I have. I can't see below, but yeah, I mean, then 11.5 is big and heavy to get us into statistical applications, but it uses what we did in 11.2. But 11.3, yeah, I'm treating it fairly lightly. I mean, it's again, if you don't know the distribution, but we would always try hard to model that distribution and have enough data to be able to put something to it. So, but it's good, gives you an estimate. Okay, that's 11.3, maybe the shortest video ever. Hi, I'm at, actually, you can see I'm not getting internet here. I'm at the convention center. I give my talk in about an hour. Um, I thought before I just kind of finished up 11.2, and then I sent you an email though. I don't know when you'll get it because I'm having trouble connecting, but there's two problems I put on homework set 7 that don't really make sense as 11.2 problems, so I rewrote them as 11.2 problems because they're asking questions about not the sum. Let me write on my tablet. In 11.2, we're really talking about the sum of random variables, but in 11.5, we're going to be talking about the average of random variables. And so it's a slightly different, as you can see, I'm going to divide by n for an average. So the question is just slightly different. I mean, I can ask you about x bar, what's the probability the average is something, or I could ask you something about what's the probability the sum is something. So it's just a slight rewriting of the problem, and so I wrote an email to send it to you so you can see the difference. I don't care if you already understand how to do X bar problems. If you took a statistics class, this probably makes sense to you. If not, this will follow exactly from what I've been doing in 11.2, and I will show you another example of those. So I was here yesterday. I was just saying if you use moment generating functions, there's a lot of nice facts. And in general, anytime you sum a large enough number, which large kind of depends on the random variable, the sum of them, so if I sum so many random variables together, you start getting a bell-shaped curve. Because if you think about it, when you sum things, even if a few values are extreme, you'll still get around the average. I mean, overall, you know, you sum enough things and you'll probably get around the same value because you're gonna sum away outliers, and you start eventually getting down to a bell curve when you sum enough of these guys. So, you know, in statistics we say you need to sum 30 of them, but if you had me before or know this is not necessarily true. I'll show you a few pictures. Unfortunately, I can't get my exponential to work right now. I don't know, maybe I don't have enough power in my Maple, but I know I changed my code, so I can show you number 1 and number 2, and I gotta run 3. 3 takes like all day to run to get the Maple to do the values. So here I'm just showing you, if you have continuous random variables, they will converge to a normal when n gets big. So remember, a uniform is just equally likely anywhere, let's say between 0 and 4. If you add 2 uniforms, you actually get something. So imagine you have one of those uniforms and you add 2 of them together. Well, you're going to get values equally likely between 0 and 4, but what's going to happen is the most likely value to get would be, right, something in the middle here at 2. So when you add 2 of them together, you start getting the shape, a triangular, that goes from 0 to 8. 8 is least likely and 0 is least likely because you would need 2 zeros or 2 4s to sum. But think of all the ways you could add on both sides of, both sides of 2 and get a number that adds up to 4. So 2 uniforms give you a triangular. When you add one more in, you still get something similar, but it starts to curve a little bit. It just starts to flatten there at the top a little bit. You add another one, so quickly a uniform converges to a normal. Other distributions take a while. That's why I wanted you to see the exponential. You know, you start off like this. That's not what it should start at 0. It starts off like this. You add 2, you get a little bit of a bump. You add 3, you get a little bit more of a bump moving out, and then eventually you will get this nice normal curve shape. So I'll show you for the uniforms. Let's see, let's go for the continuous one. I think I even have all my code up here to show you this. I mean, adding random variables is a very difficult procedure. I mean, I wrote a program to do it. There's actually the sum of 2 uniforms gives you that triangular shape. But I wanted you to see how fast it converges to normal. So this is just one uniform random variable. right there, defined on the interval -2 to 2. And then I'm going to add two of them together, and I see a triangle. Then I'm going to add more and more and more. So I've written an animation. It's pretty cool. Let me cycle it through, and let me slow it down a bit, or else it'll go very fast. And let me play it. So N just keeps track of how many I've added together. This is just 1 and 2. I think I go up to 10. I think that's it. Okay, let's play it. So nice, isn't that beautiful? So there's 1, 2, 3, 4. So I put a normal curve there so you can judge. Again, you're just adding them. So add 2, 3, 4, 5, and you get back to normality. So add enough of anything together, and you really do get back to normality. So let's actually close that one, because that takes some energy there. No. Let's go to the discrete one. So discrete, I did a discrete uniform again. This is equally likely anywhere between, I think I did -3 to 3, and it's a uniform, so it's just sitting equally likely across here. I'm going to add 2, 3, 4. I think I go up to 10 again. I wonder if I have all the code. Yeah, see where I said be patient and wait? Yeah, that's the one with the exponential. I just can't get going. I've added 6 of them together. They started between -3 and 3, so if I add 6 of them together, it's going to go between -18 and 18. But look how fast, again, this must only go to 6, how fast it converges to normal. So let's cycle it again around. Let's slow it down. Let's play it. Nice. I mean, again, I wish I had that exponential, but I don't think I'm going to have enough computer power here to get that done, so sorry, but enough exponentials, everything will converge. So you might be like, well, what does that mean to me? And this I thought maybe I should do an example to help with what do you say, the problems in the homework. I have a little space there, so let me make a quick example. So example, okay, let x be a random variable with probability density function. Let's call it f of x equal to 2x between 0 and 1. You can check. This is a valid probability density function. It integrates to 1 over this interval. Okay, so let's add. So, I mean, this is the distribution it looks like on 0 to 1. Right, it just looks like this line here. So I'm going to take random values from this distribution and add them together. So let x1, x2, let's go up to x20, be a random sample from this distribution. So all I'm saying is you have this distribution, values are between 0 and 1. I'm just going to, I'm going to pick 20 random values from here that could be anywhere then between 0 and 1, and then what I'm going to do is sum them together. So I'm going to let W, I guess I could have called it S, but okay, W is going to be the sum of these 20 random variables. And I can assure you W, by the end of it, is going to have a nice normal shape. Okay, so I know that W will be normal. I just know. I mean, I've added 20 of these together. The new mean should be the mean plus the mean plus the mean plus the mean. So what's the mean of one of these? Let's find out. Mu is equal to 2x times x dx from 0 to 1, right? That's the definition of mu. Ooh, so this is 2x squared. So what is this going to be? X cubed 2/3 from 1 to 0. So this is 2/3, right? And if I'm adding 20 of them together, that's going to be 2/3 plus 2/3. So up here, this will be 2/3 times 20 of them, right? That should be the new mean, because each of them I should get about the mean, the mean, the mean, the mean. So that's the new mean of my normal. And the variance should be, well, first I got to find the variance of one of them. This isn't going to be, so this is going to go from 0 to 1, 2x times x squared dx minus 2/3 squared. Oh, can I go over to Maple? Oh, this is getting too long. Where is my maple? So let's say f of x is equal to 2 times x. So integrate f of x times x squared from x equals 0 to 1 minus 2/3 squared. What is this? 1/18. Okay, nicely. Let's go back here. So one of them, my pen is stuck, is 1/18. So 1/18, I can add variances. So 1/18, 1/18, 1/18. So 20 times 1/18. And I want the standard deviation, so I take the square root. So I know W is going to have a bell-shaped curve with this is the mean and this is the standard deviation. So what's the question now? What's the probability that W is going to be bigger than, let me see, I'm adding 20 of them together. Let's see, I don't know, I'm just going to make up something. What's the probability W is bigger than 15, right? The sum of, I took 20 of these in that interval and I'm adding them up. What's the probability I sum them up and they're bigger than 15? Well, I know W is normal, so I can just treat this, I can do a z-score, so 15 minus 2/3 times 20 divided by square root of 20 times 1/18. This is a probability that z is bigger than, I don't know, I didn't figure it out. Go to a z table and there's my value. So I better cut this off. I know it's getting long. Okay, so I think that if you want to see another example from 11.2, let me know. Add enough of anything together. You'll get a normal with the mean is the sum of the means, and the variance is the sum of the variances, and then I can take square root to get the standard deviation.